you. Okay, I won't read the title because it's too long, but I want just to point your attention to these figures at the bottom of the first slide. In particular, this one. This is the guy who did the work, which is my student, Andrea Schiaffino. So I start with acknowledging his efforts. And this picture tells you that I'm going to talk in reality, despite the complexity of the title, about ferroelastic domain walls. So we have we all know what a ferroic system is by now. We have a multi-domain state, and we are focusing our attention on the properties of domain walls. Domain walls are a place where some component of the order parameter switches sign from down to up, and the order parameter can be either the polarization, the magnetization, or, like in this case, the spontaneous strain. And these planes that separate two neighboring domains are regarded now as an emerging class of 2D materials with new properties that do not exist, for example, in the bulk domains. How are these properties emerging? There are two mechanisms that are active. One is what Jorge told us yesterday or 2 days ago, I don't remember. It is via competition between different order parameters. One of them vanishes at the wall, so the other can emerge. But in my talk, I would rather put my attention on the fact that there are strong gradients at the wall, and these gradients are a new type of coupling that actually can only exist in a place where the order parameter is not homogeneous, like a domain wall. And so these are a sort of can give rise to new physics. So, of course, we have a ferroelastic domain wall. So the first thing we have is a strain gradient. So we immediately think of flexoelectricity as a possible gradient coupling that can produce unusual physical effects at the wall. Flexoelectricity, let me summarize what I spoke for 1 hour on Friday. Is the coupling between an inhomogeneous strain, a strain gradient, and a macroscopic polarization, which is described by a 4th rank tensor that looks nasty. In principle, it has 54 independent components, but the nice thing is that in a cubic solid, or the cubic reference structure of a perovskite, it has only 3 independent components. One is the longitudinal one that is sketched here. One is the transverse one that corresponds to a flexural deformation. And the third one is a shear, like in a transverse acoustic phonon propagating through the material. And this looks precisely like a twin wall in a ferroelastic. And so as this one gives you, via flexoelectricity, a macroscopic polarization, we can safely say that all ferroelastic domain walls are polar. Of course, we're not only interested in the microscopic properties of a single plane immersed in a huge crystal, but we want to obtain some useful functional properties out of these mechanisms. So we would like to have a macroscopic breakdown of inversion symmetry, or a macroscopic polarization that does not average to 0. The problem is, if I have a sequence, a periodic sequence of parallel domains, of parallel twins, even if you look at it, this does not break inversion symmetry by means of the strain degrees of freedom alone. And so we can expect that we have a simple structure like that, the polarization will be overall 0. And so for this reason, in collaboration with Eckhart-Sallier, we looked for different ways of arranging the domain walls, creating defects and highly complex domain structures that would break inversion symmetry, as in this case, and would have a piezoelectric coefficient, a pyroelectric coefficient, etc., etc. But in this talk, I will show you something simpler, that even if I have a very simple basic sequence of domain walls, of parallel domain walls, I can obtain a ferroelectric arrangement of these dipoles that forms at the boundaries. So I'm focusing on strontium titanate, which is a material that you all know very well, but let me just remind you the basics that will be relevant for what I will show later. Strontium titanate is a cubic perovskite in the high temperature reference structure. It undergoes a transition below 105 K, where one of the three tilt modes condensates. And I'm speaking here of these antiphase tilts, where the oxygen octahedra rotate in antiphase to each other in all directions. And this is described by the Glaser notation A0, A0, C minus. So these, this distortion lowers the symmetry to tetragonal, and via a trilinear, let's say, quadratic coupling to the strain, we obtain a spontaneous strain too, and this is why the system is ferroelastic. So it is an improper ferroelastic, let's say. And here I have a domain wall, and the only type of ferroelastic domain walls are those that are where the order parameter is at 90 degrees. And this, you see here from the sketch that the tetragonal cell meets at the wall in a way that creates a shear strain. So what is the experimental situation or the theory regarding the polarity at the wall? Well, it is not completely developed, because the experimental evidence on the polarity at the wall itself only comes from an indirect evidence on electromagnetic resonances. And before I started this work, the only information available from the theory was based on Landau theory. And the mechanism that was considered earlier was the rotostriction combined with flexoelectricity, and this would give you a polarization, as I told you in the previous slide. But the obvious question is whether this is the end of the story, or whether there are other couplings, how this looks like when you take into account all the complexity of the microscopic lattice, etc., etc. And ab initio was still missing at the time, and this was the motivation to take on this problem. So, what do we do? Let me magnify this part of the plot here, and we have the order parameter that we can that is at 45 degrees at the wall, and we can actually think of it as a one-dimensional problem. Well, this is the normal to the wall, and we can project the order parameter into the parallel and the longitudinal components. And here, instead of considering the tetragonality of the cell, we can think in terms of a shear strain, which is just the 45 degrees rotation of the strain tensor. But anyway, we can have two types of domain walls if we look really at how the order parameter rotates at the wall. And here is what I call head-to-head, where the order parameter goes from this configuration, it passes through a vertical arrangement at the wall, and then it rotates in the other direction. Or we can have another situation where the order parameter turns this way, and it is normal to the wall right at the boundary. So these two walls are inequivalent by symmetry, even if macroscopically they look the same, because they have the same ferroelastic strain. So one problem for doing this, I want to calculate all this from first principles, but a problem to do that is that the wall is pretty thick. Actually, it is much thicker than it was previously thought in modeling. And it turns out that the thickness of the wall is of the order of 5 to 10 nanometer, which is way larger than ferroelastic walls in calcium titanate, for example, or other type of domain walls like ferroelectric domain walls, which are typically 1 unit cell thick. So this, anyway, is way too thick for a direct DFT simulation, especially if we consider that these are really low energy distortions, and so relaxing a huge structure to the degree of accuracy that you would need to really understand the physics is really impractical. So what we chose to do is to pass through an intermediate step, which somebody here in the audience would call second principles, and is starting from all the complexity of the ab initio Hamiltonian, This is not even an ab initio Hamiltonian, but it's just to give you an idea. We have a discrete lattice of atoms with interactions, electrons, wave functions. We want to build a low-energy Hamiltonian, in this case, directly a continuum Hamiltonian, where we express the relevant physics in terms of some fields and some couplings between fields. And so this is a bit complex, but I will explain to you what these terms mean and what are the most relevant for the physics in this case. In any case, how do we do this transition? The first thing is to identify the relevant continuum fields with the phonon modes at high symmetry points of the Brillouin zone, which is something that is commonly done when you do this mapping of a discrete lattice problem onto a continuum Hamiltonian. And in this case, we will need 2 points, which is the gamma point, because we need the acoustic branch, which is the way we represent the strain, and the polar modes, of course, because we're interested in polarization. But of course, this the primary order parameter is the tilt mode, which is an R point distortion. So we need to do the same exercise of, well, we need some variables that actually belong to the R point in the Brillouin zone. And also, there is this other mode that you probably haven't ever heard of, which is an antiferroelectric displacement of the titaniums that will come later in the talk. So the second thing, which is what I consider is the real technical novelty of this work, is how to extract the gradient coupling terms from an ab initio Hamiltonian. So we know ab initio is a really nice and accurate theory, but one of the things that we need in order to do ab initio calculations in most cases is to use periodic boundary conditions. Gradients break periodic boundary conditions pretty badly. And so we need to devise a way to extract this information from a calculation that is economical and feasible. And the way I do that is by doing a long wave expansion, an old tool of condensed matter physicists in the wave vector Q in a vicinity of the high symmetry point. So how does this work, for example, in a vicinity of gamma? We can plot the phonon dispersion curves from along 2 directions in reciprocal space. This is gamma x, this is gamma m, and we have the 2 relevant phonon branches that we're interested in. This is the acoustic branch, which corresponds to the displacement field. This is the polar branch. And we can do a small q expansion. What is the physical meaning of a small q expansion in these variables? Well, at q equals 0, everything is clear. We have only 2 numbers on the diagonal. If we project this dynamical matrix on the normal modes at gamma, of course, this is something I need to say. So we have this 2 by 2 matrix on the normal modes at gamma, and here we project it on these modes, and we have 0, which is the frequency of the acoustic mode here, omega square, which is the square of the frequency of the polar mode. Then when we move to order q square, we have 3 interesting numbers here that appear at the same order in q and in the same matrix, and these are respectively, on the diagonal we have, I got too excited about that. Okay. On the diagonal, we have the elastic tensor, which is the dispersion of the acoustic mode. And we have the so-called correlation of the polar modes. This is how the model dispersion looks like when I take into account only the diagonal of this matrix. If I add the off-diagonal term, then this is what happens. We have a repulsion between the 2 branches, and this repulsion is precisely what I call flexoelectricity, which is a coupling at second order in Q between the polar and the acoustic branch. Okay, so this is for gamma. We need to do the same regarding the tilts. The tilt modes have 3 degenerate directions, but we need to consider the particular geometry of our domain wall and project these tilt modes along S, which is the normal to the wall, and R, which is the parallel direction to the wall. So to model the dispersion of these modes in a vicinity of R, we use the typical Landau theory expansion, which is to take the negative harmonic coefficient, which corresponds to the imaginary frequency at R, since this is an unstable mode in the cubic reference structure. And then we add the quadratic dispersion, which is related to the gradient square of the tilt. And in particular, we can have two different components. You have the longitudinal gradient, which is described by this softer branch. And then we have the gradient of the transverse component of the tilt, which is this red branch. So you see something here which is quite odd, in the sense that regarding the longitudinal branch, the model dispersion given by this approximate Hamiltonian is essentially perfect, but there is a large discrepancy regarding the transverse, the dispersion of the transverse mode. How is that? Well, this is where this antiferroelectric mode of the titanium comes in. And the thing is that this is an R-point mode that couples at first order in Q with the gradient of the tilt. So there is a coupling. This is the Levi-Civitas tensor, the total antisymmetric tensor. And so you can think like this mode couples to the curl of the tilts. And this mode is quite strong. It lies way up there at 400 centimeters to the -1. But since this coupling is at first order in Q, it is quite strong, and it changes quite dramatically the curvature. And once I consider this mode, I get a perfect agreement with the ab initio dispersion curves. So this is gamma, this is R. Of course, we need to make a link between the two, because otherwise we'll never get a polarization out of a rotation. So we need to go beyond the harmonic limit and consider trilinear couplings that are at least trilinear. So we're looking at the third derivatives of the energy with respect to displacements. And one example of this is the rotostriction, that we need to couple the strain to the antiferrodistortive degrees of freedom. And then we have a new term which looks like the one I told you in the previous slide, only I replaced a gradient with a polarization. One thing is that I can replace a polar vector with another polar vector, and it won't change the symmetry of the coupling. So this is again an invariant, just like the previous when I had the gradient here. And then I have a third coupling, which is something that I want you to focus your attention on, which is a direct coupling between the tilt, the gradient of the tilt, and the polarization again. So these are both trilinear coupling. I call this rotopolar just because I couldn't find a better name, actually. Anyway, to calculate this is a bit difficult. We need to do some linear response calculations of finite Q phonons and interpolate and do this as a function of the uniform tilt. But anyway, it's something that can be done pretty accurately with standard linear response methods. So let's touch base with literature a little bit to see whether all I said is completely comes out of the blue, or there's something that there is some relation to some earlier work that we can use to understand better what's going on. So there are some works on strontium titanate where they detect this so-called R mode that maybe Irka knows something about. It's a mode that becomes IR active and lies at 435 centimeters to the -1. It becomes IR active only in the antiferrodistortive phase at low temperature, and otherwise it is silent. And actually in this work, it was used in monodomain samples to detect the orientation of the domain wall, because it has a particular selection rule regarding the rotation of the tilt. And actually, the thing is that this is precisely the antiferroelectric mode of the titanium. And this mechanism is how this mode, which is an R-point mode in the high temperature phase, and so it is silent, this is how it becomes IR active, because we have a finite phi, and so this acquires a dipole moment. Okay. Regarding theory, there was a nice paper by the group of Anna Morozowska a few years ago, where they looked for a whole range of gradient couplings in perovskites that might be relevant, in this case to spatially modulated structures, but also polarization at domain walls and all kind of intermode couplings in non-homogeneous structures. And this, there are in particular two couplings that they consider that have some strong relationship to what I showed you here. For example, this first coupling is precisely corresponds precisely to the antiferroelectric coupling that I showed you before, that affects the dispersion of the transverse tilt. But actually, one word of caution, because this coupling works only with the antiferroelectric displacement of the titanium. So this gradient does not couple in this way to the antiferroelectric displacement of the strontium, for example. And Irka, that knows everything about symmetry, should tell me why. But okay, and then there is this other coupling, which looks quite a bit like the rotopolar coupling, with an important difference, that here the gradient is applied to a product of the tilt angles, while here I apply the gradient to only one tilt angle. So this might look irrelevant, but actually this means that my tensor W has more information than this tensor Xi, because there is an asymmetrization involved here, that you lose some information, and some important information, that because this allows to distinguish the polarization at the two inequivalent domain walls. How am I doing with time? 7 minutes, okay. Okay. So this looks like a mess. There are lots of coupling terms popping out from everywhere. But let me do some sort of biology, some systematics of couplings. And let me start from two very simple guys, which is a product of 4 polar vectors and 2 polar vectors and 2 R-point modes, 2 axial R-point modes. So from the first one, I told you that we can replace one zone-centered polar mode at will with a gradient operator. So from this one, we can get these 3 couplings that are sort of related. They contain all 4 polar vectors. And from these ones, we can actually look at what we can make in terms of the relevant polar vectors that we consider. For example, from here, we can have P4th. From here, we have the electrorestriction, just because the gradient of a displacement is a strain. From here, we have all these couplings that are relevant at OQ square near gamma, which is flexoelectricity, elasticity, and the correlation. And here, the same way, we can get all the couplings sort of in 2 separate categories that are very simple to understand. And then there are these 2 guys that are third order, that are they have only 3 indices, only 3 guys, a gradient, a tilt, and an antiferroelectric mode, or the same with the polarization replacing the gradient. But anyway, we have 3 terms here where the polarization appears, which are linear in the polarization. And indeed, we have 3 improper mechanisms where the tilt field produces a polarization. The first is the one which we already knew, which is via rotostriction and flexoelectricity with an intermediate strain. The second one is the direct rotopolar coupling. And the third one is the antiferroelectric generating an antiferroelectric mode, and this via the trilinear mode producing a polarization. And these are at the same order in the amplitude of the tilt, so they are in principle equivalent from the quantitative point of view. Okay, some data, 5 minutes. Some results, finally. We have these three modes, these three mechanisms. So we want to know how they compare to each other and whether there is something to learn about how each of these couplings acts regarding the polarization of the two different types of domain walls. Recall that I have a head-to-head domain wall and a head-to-tail domain wall, which are represented by square or circles here. Look just at the filled symbols for now. So you can see that only flexoelectricity, as I expected, gives me the same polarization at the two walls, just because the ferroelastic degree of freedom is exactly the same. I cannot get just out of the strain a difference between these two walls. When I look at the polarization, when I introduce the rotopolar coupling, here is where this W tensor that has more information plays a role, because here you can clearly see that the two walls are separated, and then this becomes even more dramatic where I introduce the trilinear term due to the antiferroelectric degrees of freedom. So this is essentially the picture, and you see that for a qualitative understanding of what's going on, which is, by qualitative, I mean the precise ordering between the two types of walls, all three terms are necessary. Okay. This is a detail about the p-squared terms that I have no time to discuss. We can plot the polarization in real space by suppressing or putting all terms. Actually look just at the continuous curves that are the polarization profiles at the two types of walls. You can see that the polarization is quite small on this scale, but I'm simulating as if I were at 80 Kelvin, let's say. I use a tilt amplitude that corresponds roughly to the experimental 80 Kelvin STO, and this is why I have this just fractions of a microcoulomb per square centimeter. But actually, this polarization will be proportional to phi square, which grows when you go to lower temperatures, and especially to epsilon, which almost diverges at 0 temperature. So you can expect a rather larger effect at lower temperatures. The question I raised at the beginning, can we get a macroscopic polarization? Well, if I combine only head-to-head domain walls, I have an antiferroelectric pattern that with P equals 0. The same if I combine head-to-tail domain walls. But if I combine head-to-head and head-to-tail, I do get a ferroelectric domain wall with a net polarization. And this pattern does break macroscopic inversion symmetry. And if you look at it closely enough, it is just identical to a magnetic cycloid. And indeed, the coupling term, the rotopolar coupling term, is just a version of the usual Jaloshinsky-Moria interaction where I replace the magnetic degree of freedom with an antiferrodistortive tilt. Okay. Can we trust the model? Can we have a couple of minutes? Okay, this is what I told you before, that there is a large overestimation in LDA of the tilt mode, so I essentially treat the harmonic coefficient of the tilts as a sort of free parameter that I can vary and explore the results as a function of this parameter, as I don't trust it. It's anyway a scale parameter. It does not affect qualitatively the conclusions, but this parameter I can interpret it as a sort of fictitious temperature in a Landau theory context, as essentially it is linear. In usual Landau theory models, it is linear with temperature. Okay, 1 minute about the validation. I claim to have a multi-scale approach apart from this parameter that I explore, that I treat as not reliable. And I have two approximations. One is the long wave approximation, one is the soft mode approximation, and the quality of this approximation can be checked independently. So this is something that I want to stress, because it's not like picking some terms that I like and trying to get something, but it's really something that I would like to think as a continuum representation of the ab initio Hamiltonian. And what we do is actually to test this approximation against the real ab initio calculation. So we take a real frozen-in cycloid of AFD distortions, and we look at the polar distortion induced by this pattern. And this is how the DFT results for the vertical displacement of the atoms of each sublattice, actually. I don't need even to make the soft mode approximation look like. Okay, this was at the beginning when I started this work, and I didn't know yet about the trilinear coupling to the antiferroelectric mode of the titanium. And you see there is a large discrepancy. This doesn't look like at all. But once I put in the coupling with the antiferroelectric mode, this is the result, and I got a perfect matching. So sometimes this procedure of going back and forth between the two models can serve also to find new couplings, or at least to doubt that something is missing. Okay, I think I'm done, and I leave there the conclusions, and thank you for your attention.